so I am going to work through your water potential practice problems. So I want you to give it a go first. So if you haven't, pause this video, work through the problems on your own, and then come back to see if you got the right answers, or if you're confused about one, you can watch how I work it out so you know what to do next time. Yeah, that's it. Okay, well, let's go. Be patient with me, okay? So, number one, if a plant cell pressure potential equals 2 bars and its solute potential equals negative 3.5 bars, what is the resulting, oh goodness, okay, water potential? So I just put psi equals negative 3.5 bars, because remember, the formula, I'll write it up here, is water potential equals solute potential plus pressure potential. So I just plug it into the thing, plus 2 bars equals negative 1.5 bars. Circle that. So the answer to number 1 is negative 1.5 bars. All right, let me change colors. All right, number 2. The plant cell from question 1 is placed in a beaker of sugar water with the solute potential of negative 4.0 bars. In which direction will the net flow of water be? So if I've got my nice little beaker full of sugar water, then I place my cell in it, and the cell has a water potential of negative 1.5 bars, and I place it into a beaker of sugar water that has negative 4.0, and I can do this in my head. The solute plus the pressure potential, if the beaker is going to have a pressure potential of 0 because it's an open beaker. So 0 plus negative 4 bars is going to make the water potential negative 4.0 bars. And remember, it always goes from high to low, so the water is going to leave. So the net flow of water will be move out of the cell. It's going to leave the cell. It's moving from a higher to a more negative, which means there's less. Okay, so the next one. The original cell from question 1, we're still working with this cell, is placed in a beaker of sugar water with a solute potential of negative 0.15 megapascals. We have not worked with megapascals, but do not fret. We know that 1 megapascal equals 10 bars. In which direction will the net flow of water be? So I'm going to set up, if you took Mr. Lancaster, now's your time to shine. All right, so we're setting it up. If I have 0.15, negative 0.15 megapascals, and I can set that up to, we know that every 1 megapascal equals 10 bars. Scratch that out, 10 times 0.5, and we have that it is 1.5 bars. And it's negative. Make sure you do that, okay? So I'm going to drop it in my beaker. Okay, and if that cell is negative 1.5 and then the solution is negative 1.5, there's going to be no net flow. It's going to go in and out at about the same rate, so no net flow. It's at equilibrium. All right, so that's number 1, 2, and 3. Oh, Okay, I'm sorry. Number 4, the value for water potential in root tissue was found to be negative 3.3 bars. So, we have water potential is negative 3.3 bars. I like to pull out the important pieces of information. If you place this root tissue in a 0.1 molar solution of sucrose at 20 degrees Celsius in an open beaker, what is the water potential of the solution and which direction would the net flow of water be? So, we're going to be working with this formula. Negative I, CRT. So we're looking, we first have to look for the solute potential. Okay, almost all of it. All right. So we have negative 1 because it is sucrose, simple sugars, 1. And then it is 0.1 molar per liter. And then we're going to use that constant, which is 0.0831. And then all that lovely stuff that goes with it. Per liter times mole. Oh, excuse me. I missed something. Oh, crow. It's fine. It's fine. It's bars. Mole. Okay, and then 293 Kelvin, because remember we use whatever the Celsius is plus 273, and that's how we get the temperature. All right, so when you do all of that math, you get that the solute, this is of the solution, is negative 2.43 bars, because all this lovely stuff marks out. Okay, so solute plus pressure potential, which is its open beaker, so that equals 0. So the water potential outside the cell is negative 2.43, and inside is negative 3.3, because they gave that to me. Then which way is the water going to go? It's going to go from high to low, so it's going to go inside of the cell. It's going to move inside the cell, or the root tissue cell. Okay. Change of color. All right, number 5. Sodium chloride dissociates into 2 particles in water, sodium and chloride. If the solution in question 4 contained 0.1 molar sodium chloride instead of 0.1 molar sucrose, what is the water potential of the solution, and then which direction would the net flow of water be? So we're going to use that same formula, negative I CRT, but this time it's going to be negative 2, because remember sodium chloride dissociates into 2 things instead of just 1. 0.1 mole per liter, then the constant 0.0831 L times bars, mole, Kelvin, time, 293 Kelvin. Sorry, it looks kind of tacky. I was going to leave with a solute potential of negative 4.87 bars. That's going to also be its water potential because we're still in an open beaker. And then, so my cell, negative 3.3 still, because it's the same piece of root tissue. And now we're dropping it into negative 4.87 bars. So now it's going to leave the cell because negative 3.3 is larger than negative 4.87. Ta-da! Alright, so it's leaving the cell. Now we're going to do number 6. A plant cell with a solute potential of negative 7.5 bars keeps a constant volume when immersed in an open beaker solution that has a solute potential of negative 4 bars. What is the cell's pressure potential? So the way we find that is because it's at a constant volume, you're just going to find the difference between negative 7.5 and negative 4. So we're going to have negative 4 minus a negative 7.5. These are bars. So plus or minus equals 3.5 bars is the pressure potential. That's it. One more question. All right, let me just change my words. All right, at 20 degrees Celsius, a plant cell containing 0.6 molar glucose is in equilibrium with its surrounding solution containing a 0.5 molar glucose in an open container. What is the cell's potential pressure? So our ultimate answer is going to be the cell's potential pressure. So we have more information for the solution than we do for the cell, so we're going to do the math for the solution first. So the solution is we're going to use water potential equals solute potential plus pressure potential. So we have negative 1 times 0.5 moles per liter times that constant. Kelvin times 293. Okay. And then that's all going to be plus 0 because the pressure potential is 0 because it's an open beaker. And that's going to equal negative 12.2 bars. So the solution water potential is negative 12.2 bars. That's not what they asked for. They want to know the cell's pressure potential. So I'm going to go back to blue. So the cell at equilibrium is going to be negative 12.2 bars. I know this is a lot of reading. I'm sorry, guys. Because it's like equilibrium, we're going to put the 12.2 on this side. Plus 1 times 0.6 moles per liter times the constant. $293K. So we're going to have negative 12.2 bars minus negative 14.6 bars, which was the answer to all this mess. So plus a plus equals 2.4 bars. And that's your answer. 2.4 bars. Blech. All right. That's it. Make changes to yours before you submit it.